In this video, I want to teach you how I learned statistics quickly and deeply. I've been working at my job for 4 months now, and it showed me that there's still an ocean of topics that I don't know about, and that I needed to know about them yesterday. Learning on the job is expected, but I've seen that people who can do this fast are the ones that get noticed and make the most impact. I'm developing my own workflow for doing this, and I wanted to share it with you today. Whether you're already experienced with statistics or a total beginner, I think there's something here for everyone, especially since we're all grappling with the presence of AI in our lives. If you're new here, my name's Christian and this is Very Normal, a channel for making you better at statistics. Let's get started. I got the idea for this video because I was recently asked to use a model that, up until then, I'd literally never heard of. It's called ANCOVA, or Analysis of Covariance. Maybe you've heard of it before. I hadn't. I've already gone through the process of learning it at work, but I made it a point to take notes throughout my entire process. What you'll be seeing is my literal thought process while I'm learning. The first step in my process is to get some sort of formula or representation of the model. If I need to use it, then I should know what it looks like and what it's saying, right? My go-to place is Wikipedia, so I'll just look up ANCOVA Wikipedia and go to the page for that model. This will work for very common models, but for something more niche or cutting edge, then I'd probably look to a textbook or the paper that proposed it. According to Wikipedia, ANCOVA is a general linear model that blends ANOVA and regression. I'm not really sure what blending means, but this at least gives me a solid background. I know that ANOVA can be viewed as a special case of linear regression, so maybe ANCOVA is the same as well. It compares whether the mean of a dependent variable are equal across one or more categorical covariates and one or more continuous variables. And the hypothesis test compares many means together at the same time. That's pretty similar to an ANOVA. Then they go into some intuition stuff, which I don't need right now. I just need the model specification right here. So here's what we got. I see there's a Yij here, so it's an outcome with 2 indices. And there's also an Xij here. So I assume that represents a covariate that has an association with the outcome, the continuous one mentioned above. There's also this weird X bar, which usually indicates some sort of average. So I'm guessing this term indicates that all the covariates are mean-centered in some way. Then there are the parameters. There's a mu here, a tau here with an I index, a capital B, that's paired with the covariate, and finally an epsilon term, which usually indicates some noise that makes it hard to distinguish between group means. Notably, mu and capital B don't have group indices, but tau and epsilon do. So I know what things will differ between groups and which will be the same. And now that I know what they are, I need to go back to the article to see how I should interpret them. So J represents the index for the observation within the ith categorical group. I is for group, J is for a particular outcome in the group. Mu is a grand mean. It's like the average of all the outcomes across all the groups. So I think the X bar is also some sort of grand covariate mean. Tau is described to be the effect of being in the ith category. In statistics, effect usually refers to some sort of change. So tau represents how being a part of one group changes their average relative to the grand mean. In my field of biostatistics, this usually has to do with comparing a placebo group against a treatment group. Here it's comparing a group mean versus the grand mean, so it's slightly different, but similar idea. This tells me that tau is actually the parameter of interest here, since it tells us how the groups differ in some way. B captures the change in the average outcome associated with the covariates. The B here is more so to adjust for the effect of these continuous variables. And this epsilon term just seems like an error term, similar to other regression models. I got what I needed for this step, but it doesn't hurt to scan the rest of the article. There's this pie chart here, which is a mortal sin against visualization. No, there's a nice plot here. I don't really like this way of visualizing linear regression, but it keys me into what the model is saying. All the groups here experience the same change in the outcome for a change in the covariate. That's reflected in the B term. In this plot, the group means are different when x equals 0, but the article specifically says that it tests whether or not these are the same. So under the null hypothesis, the plot should look like this, while the original form represents an alternative where they're all different. I read through this article with a lot of my own background information, but another way you can do it was with AI. While I have a lot of reservations about using AI, I think that this step is a good use case. I usually use Raycast to do this. If I just ask AI about ANCOVA here, it spews out a bunch of stuff I don't quite need yet, but I do see the model specification here. If I take this and compare it against the Wikipedia version, I can see what parameters correspond to what and how I should interpret them. Hey, Editor Christian here. For some of you, some of the things I'm pointing out won't make sense to you because you won't share the same background knowledge as me. And I'm sorry if you don't quite understand everything, but the point of this video is to show you my learning process, not to teach you ANCOVA specifically. If you could just take one thing away from this video, I hope it's that fast and deep learning comes from developing a dense network of knowledge and adding to it over time. This video showcases specific actions and questions that I ask myself to cultivate that. It might look different case to case, but this is the general process. An unfortunate byproduct of turning this into a video is that it can give the illusion that this process only takes a few minutes. But in reality, I spent the good part of a workday going through this entire process. More difficult concepts have taken several days even. The next step in my process is to find actual use cases for the thing I'm learning. Step 1 provides a purely statistical view of the model, but I need to be able to apply it to specific projects and understand how to talk about it. The Wikipedia article did provide a use case, but there's no numbers associated with it, and it's not in my industry. I work as a statistician in the pharmaceutical industry, so the most natural examples that I look to are clinical trials. Clinical trials are a great place to learn from because they're highly regulated, which means that the statistical rigor expected from them is much higher. Recently, I've been seeing a lot of news about Novo Nordisk. They're the company behind one of the most consequential drugs developed in recent times. The technical name for Ozempic is semaglutide, or as I'll be calling it throughout the video, SEMA. One of the most important trials for SEMA was the Step 1 trial. Step 1 was a part of Novo Nordisk's registration package to get SEMA approved in the United States, and it specifically looked at weight loss in the obese and overweight population, measured as a % change in the weight compared to baseline. Of course, Novo Nordisk was interested in proving that SEMA would result in more weight loss compared to placebo. What I'm showing here is the original manuscript written to showcase Step 1 results, and you can find this just by Googling it. But another good resource is clinicaltrials.gov, which is the world's largest publicly accessible repository for clinical trial information. What's really nice about this site is that the companies will often post the results of their trial and describe their statistical analyses in excruciating detail. If I click on the results posted tab, you can see all of them. If you want to become a statistician in pharma, this is a very good way to check your knowledge. If I search the page for ANCOVA, then I'll see that it appears in 2 places. It was used in Statistical Analyses 1 and 2, which both compared SEMA against placebo for weight loss. I could see that they estimated that SEMA produced a 12% drop in weight adjusted for a placebo. So this negative 12% has to correspond to somewhere in the ANCOVA model. Since treatment group is categorical, it most likely corresponds to the tau. This is the parameter that Novo Nordisk would be the most interested in, and seeing that it had a low p-value. But looking at the model, there should be some covariates added to the ANCOVA. So for completeness, I want to know what they are. I couldn't find them on clinicaltrials.gov, so I went back to the published manuscript for the trial. Since tau is the main thing that Novo Nordisk would want to report, it's unlikely that they would report the coefficients for the other covariates. They're more for adjustment. After reading through the document, I found what I was looking for. Table 2 summarizes the information on all their primary and secondary endpoints, and in the footnotes, you can see this. Continuous endpoint analyses were conducted with the analysis of covariance method, with randomized treatment as a factor and baseline endpoint value as a covariate. So they adjusted for a single covariate in their ANCOVA, and it was the baseline measurement for each endpoint. This would control for the fact that everyone in the trial starts at a different weight, and I can see how this might influence how much weight they would lose throughout the trial. Furthermore, I want to highlight the slight change in notation here. Instead of using a grand mean mu, I've changed it with a beta 0 to represent the weight of the placebo group. Novo Nordisk was interested in seeing how well the treatment compared to placebo, not against a grand mean, hence the switch. However, this was an ANCOVA with only 2 groups, placebo and SEMA. The Wikipedia article made it sound like ANCOVA could easily account for more than 2 groups, and I wanted to see how a company might report something like that. To save you some time, I'll just show you the example that I ended up finding. It was another SEMA study, except this one was done in people who have type 2 diabetes. Specifically, Novo Nordisk was trying to figure out how blood sugar and blood weight change with multiple doses of SEMA, 2, 8, and 16 milligrams, while comparing them to a 4th group, placebo. In the results section, they clearly posted ANCOVA in the analysis approach, but this time you can see that there's multiple comparisons against placebo. Here's one for 2, one for 8, and one for 16 milligrams. Each of these numbers represent a different tau in the ANCOVA. And thankfully, they made it easier to see what specific covariates were included in the model: sex and baseline HbA1c. To be honest, when I was still learning, I didn't even know that Novo Nordisk had used ANCOVA in their trials. I literally just looked up semaglutide on Google and got lucky with the first results. But you can do this with other companies as well. Step 3 in my process is to start working with code. The first 2 steps really involve being a statistics consumer, just reading about and understanding the model itself. But ultimately, I'm going to need to be able to use it in my own projects, so I need to be a statistics user. This means I need to be familiar with the statistical programming for ANCOVA. Similar to step 1, this can be done by either Googling R ANCOVA or Python ANCOVA, or you can just ask AI for a faster answer that you might need to check. If AI is good at anything, it's at providing code advice. Claude tells me that the AOV function implements ANCOVA, and it even gives me a helpful example to copy. Claude also tells me that I can use linear regression as well, which I already suspected. I've never used this AOV function before, so I'm going to dig into it a little bit more. The way I do this is by reading the documentation for the function. Sometimes online posts can be helpful as well, but in my experience, the documentation plus AI will get you most of the way there. The documentation tells me that the AOV fits an analysis of variance model, an ANOVA model. Furthermore, it just tells me that it uses the LM model, which implements linear regression. Should I be concerned? Not really. One of the unfortunate things about statistics is that a single model might be given multiple names. This is why it's important to look at the model specification first. In the end, ANCOVA really is just a linear regression with a specific set of covariates, a categorical variable of interest, and possibly many covariates that can either be categorical or continuous. So in that respect, Wikipedia was actually sort of wrong here. It focuses on the nature of the data itself rather than the question it can answer. This is why looking at the real-world examples is important too. Looking at the example Claude gave us, we can see that it uses a formula expression, where we can specify what variable is the dependent variable and which are the covariates. But the one thing we don't have is data, so this makes it hard to really interact with this piece of code. This leads us to the final step. Using the code that Claude gave me earlier, I'm going to ask it to generate me some simulated data. To better match the data from the STEP trial, I'll ask it to generate just 2 groups and just use one covariate. I'm going to take the code that Claude generated and jump right in the posit so I can play around with it. It helps me to frame the groups in a way that I'm used to seeing them, so I'm going to change the group names to placebo and sema. This code is for the outcome. Based on the way that Claude has commented the code, it looks like they've coded it in terms of a linear regression rather than on ANCOVA. This 30 corresponds to the intercept, and this 10 corresponds to the change in mean associated with being in the sema group relative to the placebo group, and this 0.05 represents the covariate shift. Then this R norm must be the epsilon. By looking at the data, I can see that it's generated such that the placebo group and the sema group will have different means. In other words, it generates data according to a specific alternative hypothesis. In this case, we should see the ANCOVA should reject the null hypothesis. If I run this model that Claude gave me and check it via the summary function, then I can see that that's really the case. The output is organized more like an ANOVA rather than a linear regression, so the p-value I need to look for is the one associated with this F statistic here. Even though the statistic is calculated with variances, it's still based on the hypothesis that the means of the placebo group and sema group are the same, so it still applies here. With this code in hand, I can play around with the values and see how it affects the analysis. For example, if I change the standard deviation to 20, then the effect size associated with being in the sema group goes from 2 to 1/2. It should be much harder to reject the null hypothesis because the variance around the group means is much higher, so it's harder to resolve them. If I repeat this code, then I can see that we actually fail to reject the null hypothesis in the case, like I suspected. But I know that this will depend on the particular data that was generated, so I can repeat this a few times to get a feel for how often it happens. You can also play around with the sample size of your data or the effect associated with sema. It's all code on your local computer, so it doesn't cost money to change things around, unlike with the real data set. The main point is that programming gives you a way to actually interact with the model and see how you can alter the result it pops out. A lot of people get stuck on not being able to do statistics without data, so simulated data offers a much needed bridge for learning. Like I mentioned earlier in this video, the key to developing fast, deep knowledge is to develop a network of knowledge. Here, I started with a basic model specification and connected it to actual use cases. From there, I figured out how to actually use the model in code, and I played around with some simulated data. And all along the way, I tried to connect it back to things that I already knew so that no concept lays totally in isolation in your mind. Done right, this type of learning forms a virtuous cycle, where your current knowledge makes it easier and faster to pick up new things. Even if you don't have the same level of background knowledge as me, everyone has to start somewhere. You can still try to connect new models and techniques back to your own experiences. For statistics specifically, the process I've covered here forms a good base to start. As a last note, let's talk about AI. What you get from AI does not replace true, deep understanding. If you're a beginner, then I caution against only using AI in your learning. Learning is supposed to be a slow, painful process, and AI can totally take that away from you. I got slightly different opinions from Wikipedia and AI, so it was up to me to reconcile the differences between them. I hope you're able to pick up some new tips and tricks from me and be more prepared for your statistics journey. If you enjoyed this video, I hope that you'll subscribe to the channel for more content like this. You can stay up to date by signing up for the channel newsletter, where you'll get notified every time I upload a video. I hope that you learned something new today. Thanks for watching. I'll see you in the next one.